Welcome back. Now we'll look at the next Unit 1 topic, which as you can see is binary coded decimal, or shortened as BCD. So, what we're going to look at in this video, one is going to be accuracy issues with storing decimals in binary, and yeah, we'll see how there's some numbers or some decimals that we can represent in base 10, okay, but we can't represent in binary. And well, I suppose when I say binary, yeah, this is just talking about kind of regular, fixed point, floating point decimal binary. Then we'll look at how binary coded decimal, or BCD, addresses and fixes this. Then we'll look at BCD addition. And finally, we're going to look at the advantages, disadvantages, and use cases of BCD. So if we look at, fixed or floating point problems, so actually how to calculate fixed and floating point is not required for A level. I suppose, okay, actually, this should say AS, because, for A2 this is required, but yeah, not for AS. However, we do need to know one issue with it. And that is, basically, yeah, we can represent some non-integer numbers accurately. And I think, yeah, let's see an example. So here, if we have, 0.1 plus 0.2, now, of course, in maths, we're going to expect that's going to be 0.3. So yeah, we would expect it's going to output 0.3. But if we actually execute this, this is actually going to be the output we get. And, yeah, I guess maybe some people can recognize, this is the Pseudocode website. But, this actually happens in every programming language. So that's also going to happen in Java, Python, Visual Basic, C, C++, Pascal, etc. And the reason that happens in every language, I suppose, unless they'd specifically designed a way, to sort of, I guess, yeah, to use BCD or a different representation. The reason it happens in every language is because, basically this addition, it's not the programming language that's actually performing this addition, This is actually the processor. So yeah, this is the native, I guess just the native add instruction within the CPU. So yeah, if we just go next, and then let's see how we can actually represent 9.75 in fixed point binary. And again, this is not required for AS, but I think it's useful to see, because if we know how to represent it, then we can see, I guess, yeah, then we can see the problem with it. So if we think, of course, yeah, just in binary, as we go left, we say what the power is increasing, so 2 to the power 0, 2 to the power 1, 2 to the power 2. Therefore, of course, the actual value that represents is going to double. In contrast, if we go right, here, of course, we go from 0, then to the power of minus 1, or a half, then to the power of minus 2, or of course a quarter. So if, for example, let's say we want to represent 0.75, that means, we are, of course, we need a 0.5, then, yeah, plus a 0.25. So technically, a modern computer is going to use a slightly different method, floating point, and in this case, the binary point can actually move. But yeah, I guess overall it's quite similar. Where again, we're still going to have this same thing. So as we're going it's just going to go 2 to the power 1, 2 to the power 2. The only difference is that I guess same with sort of scientific notation. Of course, we could write 3 times 10 to the power of 8, or equivalently, we could also write, say, 300 times 10 to the power of 6, And of course, they're going to be equivalent. It's kind of the same thing in binary, where, yeah, basically, we can just move this binary point, left and right. But again, it's still going to have the same problem of, of course, having these values like, 0.5, 0.25. So something like this, then, let's say 0.2489. Maybe we can't actually represent that properly. Because if you think, I guess 0.42, 0.5 is too big. Of course, yeah, I guess we will need a 0.25. Then we're going to need a 0.125. That's going to get us to 0.375. Then I don't know. Yeah, I guess maybe we're going to need the next one, or the next one. But if we add all of those up, maybe we're only going to get something like this. So let's think then, is binary just bad, or does this problem also occur in other bases like base 10? So if you've paused the video and have a think, then yeah, actually this is going to be yes. So again, pause the video, try to think of an example in base 10 of a number that even with an infinite number of digits, we still can't accurately represent. So if you want an easy one, I guess 1/3, that's probably the most simple one. Because of course, it's just going to be 0.3 recurring, an infinite number of decimal places. An infinite number of digits. I guess another one, just the square root of 2, pi, of course, e. And if you think about it, let's think how many numbers can be accurately represented in denary. And if you think about that, well, of course, it's going to be an infinite number. And the reason for that is, well, of course, you can have 1/3, but then you can also have 2/3. You can have 4/3. Yeah, of course, 5/3, right, 7/3, right, etc. Yeah, of course, well, likewise, well, yeah, of course, you have, square root of 2, but then square root of 2 plus 1, right, square root of 2 plus 2. But if, yeah, I guess, well, let's think in contrast, right, what base could represent 1/3 correctly? And if we think, well, that's going to be what, base 3, because, of course, what we're going to have 3 to the power of 0 here, but then we're going to have 3 to the power of minus 1, and, of course, yeah, 3 to the power of 1 is going to be, well, 1/3. So, I mean, really, we're saying, well, binary is not actually the problem. Of course, yeah, every base is going to have some numbers that it can accurately represent. But if we're just, yeah, so I suppose, okay, right, if we're just looking at kind of accurately representing base 10, right, in binary, then, well, that's how we can use BCD. So if, for example, if we want to represent 0.3, which, of course, we can represent in, yeah, I guess in denary, then, well, we're going to use BCD to actually, let's say, accurately represent this in binary. So the way this works, it's actually similar to hexadecimal like we've seen before, where we're going to represent each digit independently, and we're going to use 4 bits. So, right, e.g., 729 will be represented as follows. And note the first digit isn't negative like in 2's complement, right? We're always going to use unsigned for BCD. So if we think, okay, so, well, yeah, let's just write the positional values, right? Of course, well, 1, 2, 4, and 8, right? Just the same as regular binary. So, of course, well, this is going to be 7, right? Because, of course, well, 4 plus 2 plus 1, right? Just, yeah, regular binary. The next one, again, right, well, 8, 2, right, 4, and then 1. So, of course, well, to get 2, it's just going to be the 2. And then, of course, here, well, yeah, also, right, 8, 4, 2, and 1. Right, therefore, well, 8 plus 1, right, that's going to get us 9. Now, that's also similar to hexadecimal in the fact that, well, let's say, I don't know, maybe we have A4, let's try, yeah, B or something. So of course, what we're going to do, right, we're going to break this, or, okay, well, all right, let's say we're going to convert each hex digit, right, into 4 bits, or, yeah, each hex digit into a nibble. And, of course, well, A, right, so what A is going to be 10, right, therefore, that's going to be this. Well, 4 is just going to be, well, 4 like that. And then, well, B, that's going to be 11, so... yeah, that should be like that. So yeah, hopefully you can see how this works again, just breaking down each digit into 4 bits. Yeah, and of course, well, in contrast, like, let's say if we want to represent, I don't know, well, yeah, okay, well, let's just say 12. So to represent, 12 in binary, like, of course, we're going to store that as a single number, so it's just going to be this, right, yeah, 8 plus 4. Now, to represent 12 in, to represent 12 in BCD, okay, we're actually going to store that as 2 separate numbers. So we would store, well, 1, of course, is just going to be, just 1 like that. Right, then the next digit, well, that's just going to be 2 like this. Yeah, okay, so, well, I think, yeah, we've mentioned that, right, just representing each digit, right, independently with 4 bits. Right, then there's going to be 2 types. So one is unpacked, and unpacked binary coded decimal, this is going to use 8 bits or 1 byte to represent 1 denary digit. Right, then there's going to be packed binary coded decimal, and that's going to use 4 bits or, well, 1 nibble to represent 1 denary digit. So to this, to see an example, well, unpacked, and the thing to notice here is that, well, because BCD can, BCD only has the range 0 to 9, right, of course, yeah, just the denary digits, then to represent 0 to 9, well, in binary, well, that's going to be 4 zeros, up until this. So what we're saying is that, well, effectively, right, these first 4 bits, okay, they're always going to be 0. Likewise, of course, on the second digit, right, these first 4 bits, they're always going to be 0. So yeah, hopefully you can see a problem with that. Right, then we've got, well, packed BCD, and packed BCD, this is the one we've seen, where, like here we're, of course, not just having that wasted space. So in this case, well, we're only using 4 bits, right, we're not wasting the extra 4 bits as well. Right, so let's think then, well, what therefore are the advantages of packed BCD? And remember, well, packed BCD was the second one. So yeah, hopefully it's going to be fairly obvious. Well, one is going to be more space efficient because it's only going to use half the bits. Right, then another advantage, so this one I put in orange because, well, yeah, possibly it's going to be faster. And the reason I say possibly is because, well, I guess, like, let's say you're doing some sort of addition. Now, in this case with, like, even with unpacked, right, you only have to focus on these 4 bits at a time, right? Of course, yeah, you can just, ignore these 4. Likewise with this 8, okay, right, you only have to focus on these 4. So it's not like you're actually doing the operation on all 8 bits, right? You're only doing the operation on 4 bits. which of course is just the same here, right, where you're doing the operation on, 4 and 4. So this is why, maybe it's faster, maybe it's not. Like in the exam, of course, if they ask what's the advantages of packed BCD, just go with this, right, more space efficient. Well, I guess you say, okay, let's say uses less memory, or that should be fine. Right, so this is often a question, this is a question they often kind of ask. So they give you a number and they say, would this be a valid BCD number? So again, right, pause the video, have a think. And if you've had a think, well, let's just think, right, okay, no, and well, that's going to be 12. And if we remember that, of course, in BCD, we can only represent 0 to 9. And I think this one we've actually mentioned before. See if you remember, right, so how would we actually represent 12 in packed BCD? So remember, when it says packed BCD, well, this just means use 4 bits, right, for each digit. Therefore, of course, first we're just going to represent the digit 1, right, then the digit 2, and of course, just represent them independently. So hopefully that makes sense. Right, then if we think using packed BCD, how many bit patterns are wasted? So, just to recap again, we said, from 0 to 9, so 9 is going to be this. Right, of course, these are going to be the valid ones. Right, therefore the invalid ones, right, it's going to be from 10, 10 to 15. So in that case, hopefully you can see what it's going to be 6 bit patterns that are wasted. And I suppose if you think about that, it's going to be 6 out of 16 are wasted, which I don't know, is that like maybe 40%, or like approximately like 30-40%. It's quite a significant number. Right, then if we look at decimals, so we can also represent decimals in BCD in the same way, and I guess that's kind of the whole point, right? Binary coded decimal. Right, so what this is saying is, BCD is not standardized, so things like, floating point, fixed point, okay, there's actually standards. When I say standards, I mean, you can think of that kind of like a protocol, in the sense that basically you say, there's rules between manufacturers. So whether you're using an Intel, whether you're using like an ARM, right, AMD, of course, they're all going to use the same representation of, fixed point and floating point, right? Therefore, that's why, of course, these devices can actually communicate with each other. Likewise, of course, programming languages, right, they're going to use the same representation. Right, in contrast, BCD is not standardized. So that means that, different hardware, right, different software, okay, they're going to have different implementations. And in some ways that's good because, of course, you can sort of, customize the implementation, for your specific need. But because of that, we're saying, there has to be a way of, how do we actually represent where the decimal point is? Because, of course, if you had, let's say, 9.236, right, that's obviously a different number to if we had, 923.6. So, of course, there has to be a way of representing the decimal somehow. And again, right, if we just ignore the decimal, hopefully you can see how we get this, right, just, the 9, then the 2, then the 3, then the 6. So we said that, only the single digits 0 to 9 are valid in BCD, right? Can you then think of a clever way that we can represent a decimal point in BCD? And again, right, if you pause the video, have a think. So hopefully you can realize, we can just use one of the unused bit patterns. And probably an obvious candidate is just going to be 4 ones. Since, I suppose that's going to stand out, right? It's going to sort of be unique. It's going to be, let's say, easy to spot, right, if you're just reading it. So in that case, if we wanted to represent 7.5, right, then of course we can just represent it as this, right, 7, then of course the 4 ones for the decimal point, then of course the 5. And again, right, of course, different developers have different approaches, but this could be a possible approach. Now, in the exam, they would never ask you to do this again. I mean, of course, because it's not standardized. Now, in theory, they could ask you, how could you possibly represent a decimal? And then you say, you could use one of the unused bit patterns. But honestly, I feel the chance of them asking that is less than 1%. That would be a quite difficult and quite strange question for them to ask, to be honest. Right, so again, right, this, I've also never seen this in the exam. I mean, maybe 10 years ago on the old syllabus they might have asked it, but certainly in the new syllabus I've never seen it. However, this isn't, this is in the book, right, so let's look at how to do it. Now, there's going to be 3 stages. The first stage is quite easy. We're just going to add 2 BCD numbers, right, the same as we would if it's just regular binary addition. Right, then we say if the 4-bit sum is less than or equal to 9, so effectively if it's a valid BCD number, then it's valid, right, then we just do nothing with it. Just kind of leave it as it is. Right, however, if it's greater than 9, or if a carry out is generated from the 4-bit sum, then we want to add 6 to it. And the reason we add 6, okay, I mean, well, yeah, basically we'll see that on the next slide, but it's to skip these 6 invalid states. So if a carry out, or okay, sorry, right, if yeah, okay, yeah, so if a carry out occurs, then we add the carry to the next 4 bits or nibble. And the reason for that is because, well, if a carry out has occurred, right, let's say if we got, what, 8 plus 8. Now, of course, what, 8 plus 8, well, that's going to be, what, 4 zeros. But then, of course, we have a carry out in this position. So really what we're saying is, well, yeah, kind of like our real answer is 16. So because, well, 16 is therefore, you know, bigger than 9, right, it's not in our range. Yeah, that's kind of why we're saying, well, we then have to add this, right, to the next digit. So, well, let's just try this then with 7 plus 5. Right, so the first stage, well, we just add the 2 BC numbers using regular binary addition. So hopefully we're familiar with this now, right? 1 plus 1, right, that's going to be 0, and then we'll carry the 1. Right, and then, well, 1 plus 1 plus 0, again, well, 0, right, carry the 1. Alright, then we've got 3 1s, so we've got a sum of 1, right, then carry of 1. And then here we've got a 1 and 2 zeros, right, so just a sum of 1. Now, if we look at this, well, of course, right, well, 8, 4, 2, 1. Right, therefore, our answer here is going to be 12. And 12 is bigger than 9, right, so this is going to be an invalid BCD digit. So yeah, what we then need to do, well, we then need to add 6 to circle back around. So actually here we can see this. So let's say, for example, if we're, okay, so yeah, we were on 12. So if we add 6 to this, right, so well, 1, 2, 3, 4, 5, 6. So, right, that's going to get us back to 2. And effectively what you can think of this, I mean, basically it's just kind of like deleting that first one, right? It's just deleting the first digit. So if we're on 2, or okay, sorry, if we're on 12, right, then we're going to get back to 2. If, for example, we're on 14, right, then we're, you know, going to go to 4. So again, it's just kind of deleting that first digit, right? That's really what it's doing. And equivalently, like, you can also think of this as being equivalent as minus 10. Like, for example, if we're on, what, 11, and then, sorry, yeah, if we go sort of minus 10 from 11, right, that's going to get us back here to minus 1. Yeah, so hopefully that makes sense. So if we do that, well, we take our previous answer, which, well, remember we said was 12. Right, then we just add 6 to it. So, of course, well, 0 plus 0 is 0, 0 plus 1, that's 1. 1 plus 1, again, well, yes, sum of 0, carry of 1. Right, then we've got, what, 1 plus 0. Again, right, a sum of 0, right, but then, well, in this case, another carry of 1. So here we see, well, okay, right, so this is 2. So, of course, yeah, well, okay, so this part is fine. But, again, since, again, we've got this carry, well, then, again, we have to then go into the next column. Yeah, okay, we have to add this to the next nibble. So what we do, well, we take our carry out, and I suppose in this case, like, I mean, basically, what, 7 plus 5, of course, what it's saying we've got, yeah, 0 in this column, right, 0 in this column. Therefore, of course, well, they're just going to be zeros, right, and then there's only going to be our carry out from the previous digit. So effectively, we just got this, well, yeah, of course, right, 1 plus 0, right, it's just 1, and then obviously all zeros. So if we then combine this with our first result, well, we say, right, so yeah, this is going to be our first digit, which is 1. Right, this is our second digit, which is 2. And then, of course, well, 7 plus 5, yeah, that's going to be 12. All right, so again, yeah, well, 1, then 2. So this is maybe a little bit tricky. But, yeah, I think if you go back and watch that again, right, try to understand it. Because, well, I think, yeah, now with that, I guess now I'll have a look at a yeah, sort of bigger example. Right, so let's try and do the whole thing. So here we're doing, what, 0.26 plus 0.85. So first then, well, we're just going to add this 6 and 5. So if we do this, well, I guess, yeah, of course, well, this is going to be our 6 here. Right, this is going to be our 5. Right, if we add those, right, then we should get this. Now, here we want to think, well, this is going to be 11. And, like, well, of course, I mean, that's correct, right? 6 plus 5 is 11, so yeah, that's fine. But, of course, since that's bigger than 9, well, therefore, we need to add 6 to that. So here then, well, yeah, basically, I've just rewritten this. So, yeah, this green thing, right, I've just rewritten it here for the new sum. Right, then this is our 6, so here we're just adding 6 to this. And of course, right, if we do that, well, then we're going to get a 1, which is fine. Right, then we also get a 1 here in the carry position. Yeah, okay, so that's fine. So what we then do, well, yeah, hang on, right, so, well, right, okay, so right now, since we've done this digit, or, well, yeah, right, of course, yeah, we've done the 6 plus 5. Right, then we want to go to the, well, the sort of, yeah, the next digits, right, so, well, that's 2 and 8. So yeah, let's just go here then. Right, so of course, right, if we look at this, so well, this is going to be our 2. Right, of course, yeah, well, this one here, this is going to be our 8. And again, that's, well, that, yeah, I think, right, this was 0.26, right, this was 0.285. Yeah, I think I've kind of like graffitied all over this now. Right, so of course, well, right, then we're just going to add these, right, the 2 and the 8, okay, but we're also adding our carry, yeah, from this, previous answer. Right, then if we add that, well, again, that's also going to give us 11 by the looks of it. Well, of course, right then again, we're going to think, well, 11 is too big, right, therefore we need to add 6 to it, right, since it's bigger than 9. So again, right, this is our 11 here, right, the previous answer, right, of course, well, this is our 6. If we add those, I guess, right, that's going to give us 1 here, but then it's also going to give us a carry. And then in this case, well, we then just want to add that. And I suppose technically, like, we should probably do 4 zeros here. Since, yeah, I guess, well, we are saying, right, like 0.26, right? And, well, then, of course, we're just going to add all those together. So, yeah, well, we're just going to be adding this 1, right, with, of course, all of these zeros. And, yeah, that's just going to give us 1. So if we do that, well, that's going to give us 1 for this first digit. And, I mean, here I've just put the point. Yeah, like, I've not bothered to represent the decimal point here because... well, yeah, I guess, in the exam, they're not going to do that. And then, of course, well, yeah, this is a 1, right, and then this is a 1. Right, so I think, all right, let's try this one by ourselves. So, hang on the rate, 0.93, and then, all right, let's do it here, 0.58. And actually, like, the good thing with this, of course, well, we can actually just do this in denary. So let's check, well, this is going to be a 1, right, well, then we're going to carry the 1, and then, well, that's going to be a 5, and then, well, that's going to be a 1 here. So I think if I've done that correctly, okay, this should be 1.51. Yeah, so I think that's correct. Right, so of course what we can do is, well, we can then, do our BCD addition, and of course, well, just check that it equals this. So that is the one thing, like, while the method is maybe a little bit complex, I mean, it is going to be really easy to check. Right, so let's just write this then. Let's write the 3 and the 8, okay, starting on the rightmost digits. So the 3 and the 8, well, that's going to be this. Right, the 8, well, that's going to be this. Right, then we're going to add those, so I guess, well, this one we can add quickly. Right, then we think, well, again, that's also going to be 11. Right, so then we're going to add 6 to it. So I'm just going to do it all in one go. Right, so if we add 6 to this, well, right, of course, well, yeah, this is going to be a 1. Right, here we've got 2 1s, so what is 0, and then we'll carry the 1. Here, 1 plus 1, again, right, a sum of 0, right, carry the 1. And then here, well, again, right, 2 1s, so yeah, sum of 0, right, then carry the 1. So here we can actually say, well, right, this is going to be our first digit of 1. Right, then we have the carry over from this one. Right, then we want to do what, the 9 plus 5, and then, yeah, also plus this carry. So, right, yeah, maybe I'm just going to do this here. Right, so let's say 1 here. Right, and then 9, well, that's going to be, right, that's going to be this. And then, right, 5, well, that's going to be a 0, right, then there's going to be a 4, and then there's going to be a 1. So if we add all of these, well, so 3 1s, that's going to be a 1, and then carry the 1. Right, then here, well, that's going to be a, yeah, well, okay, that's going to be a 1. Right, here it's going to be a 1, and here it's going to be a 1. Right, so in this case, well, that's 15. Yeah, which, and I guess, yeah, I mean, here we can kind of see that, right? So, of course, well, 15 is too big. So, in this case, again, we need to add 6. Right, then if we add 6 to this, well, so this is going to be a 1. Right, 1 plus 1, that's going to be 0, carry the 1. Right, 3 1s, well, that's going to be a 1. And then, yeah, okay, right, well, 1, and then carry the 1. And then, well, that's going to be a 0. And then, yeah, here also carry the 1. So, if we look at this, well, now, what, that's a 4 and a 1. So, that's going to give us our 5. Right, then here, well, we've just got a 1, and then I guess, well, again, we've got our sort of zeros. Now, if you wanted to do this formally, well, of course, you go, well, 0, 0, 0, right, 0, 0, 0. And then, of course, you just go a 1, right, then you just add them. And, of course, right, if we've got that, well, again, yeah, 151, and if we just want to add the decimal, right, that's going to be our 1.51. So, yeah, hopefully that makes sense. Right, now this one again, like, I'm not going to go through it. Okay, you can pause the video and, yeah, then, well, of course, unpause it, and then, well, I'm just going to reveal the answer. So if you do that, well, you should then get, what, 14.2. And again, of course, you can easily check this, right, just by adding them, directly in denary. Right, okay, so, yeah, I guess, well, maybe this is a difficult process to remember, and that's probably one of the reasons it's never been asked in the exam. Like, it's also not used that commonly, compared to, let's say, just regular binary addition. Yeah, of course, BCD is kind of quite rarely used. However, this is in the book. Right, and I suppose, well, yeah, I guess, if you still want to practice, of course, well, try more for homework, and you can easily check the answer yourself, yeah, as we said, by converting the BCD answer to denary. And then, of course, yeah, just do the denary calculation. Yeah, so just some other ones, right, if you want to have a go. Right, so let's then look at some of the disadvantages, because, well, we said the advantages is that we can accurately represent decimal digits, or, okay, we can accurately represent some decimal numbers. So, For example, like 0.3. Now 0.3 in binary, or I guess yeah, in regular, fixed point, floating point binary, we actually can't represent that because, well, if you remember, it's going to be what, yeah, sort of a load of zeros then a 4. Whereas of course with BCD we can, because, well, we just represent as a 0, right? Then we represent as a 3. It's kind of, yeah, two separate characters. So if BCD allows us to store decimal numbers exactly, then why don't we use it instead of 2's complement? And again, yeah, maybe just pause the video or have a guess. Yeah, I mean, like try to think of some theories. All right, so let's take a look. Well, one is going to be wasteful because we said, well, 6 of the 16 values in 4 bits aren't used, right? Therefore, if you're storing, sort of gigabytes of programs, and yeah, let's say, your loads of numbers, like potentially what your program's going to be like, what do we say, 40%? So yeah, your program's going to be like 40% bigger, or 40% wasted space. Right, it's also going to require more complex circuitry to store and perform the arithmetic. And I think addition is actually not that complex. But I think for multiplication especially, they say that, yeah, for multiplication, I guess the circuitry, right, is going to get quite complex. Compared to just binary, where I think binary, they use, basically it's using shifts, and then, yeah, it's using some, I guess some other things as well. And right, it's also going to be slower. And again, well, of course, that's because, right, you've got more complex circuitry, right? There's more instructions, more steps, right? Yeah, therefore it's slower. All right, so yeah, this is in a completely wrong order, it seems. Right, okay, so just to recap then, well, the advantage, again, right, we can store base 10 decimal numbers exactly. Right, disadvantages, well, it's wasteful, right? It's complex circuitry, right? Therefore, it's going to be slower. Then, if we look at some of the use cases, well, it can be used in digital watches. And the reason for that is because, well, if you think in a digital watch, right, we only need to store the numbers 0 to 9. So let's say, I don't know, maybe we had to say like 14, like 50, 1456. Now, like, you could do it where I guess you could just store this whole thing as just, a binary number. So yeah, you just store the whole thing as like seconds. And then from those seconds, you can then, work out how many minutes, how many hours, how many seconds, for example. But and I suppose, like, if we also want to add on the seconds, like, I don't know, let's go 25. But what you could do is, you could just store each number independently in BCD. So you say, well, 4 bits for this, I guess, hour. Yeah, 4 bits for this hour. Of course, yeah, 4 for this, 4 for this, 4 for this, 4 for this. So in that regard, it's kind of quite simple just to store it in BCD, because you don't have to do any calculations of, let's say, for example, like mod, right, or division. To work out how many, I guess to sort of convert seconds into minutes, or to convert, seconds into hours, for example. So yeah, I guess it can be quite simple in that regard. Likewise for, well, timers, stopwatches, right, alarms, any sort of timing thing. Right, it can also be used in some scientific equipment, like, let's say, voltmeters, right, also oscilloscopes. And again, well, that's because we can represent the base 10 decimal numbers exactly. So yeah, if we want kind of high accuracy, right, then I guess you can use BCD. Right, and also some programs to represent financial values exactly. Now, in some databases, right, they actually have something called a currency data type. And a currency data type, well, it's going to store a decimal point. It's going to store a number to 2 decimal points. Now, possibly this is using BCD. I guess it depends on the database, right? Some might use BCD, some might just use regular, fixed point, floating point. Because if you think, right, okay, let's say, obviously, let's say you got some financial value. Well, you wouldn't want to say add like 0.3 to your account, and actually instead it adds, 0.3, 0004. Now, actually, to be honest, like, in that case, it's probably good, right? Because, well, yeah, of course, you're going to get more money. I mean, if you were paying someone, of course, you wouldn't want to pay them more, right? Likewise, I know, like, maybe there's another one. Let's say, 0.72. And maybe that's going to have to be represented as like 0.71, 99999, like 5 or something. And then obviously in that case, well, in that case, you're going to receive less money than what you expect. So for currency, or for financial transactions, if we want to be 100% sure, to get the exact amount, right, that's of course where we can use BCD. Alright, anyway, guys, I mean, hopefully that video makes sense. Like, to be honest, they actually don't ask BCD that much in the exam. Although, yeah, of course, I mean, it is good to know, because, well, if they do, yeah, some people just, completely forget this stuff, right then they're, well, just completely lost on those questions. So yeah, as always, well, hopefully this video is useful. Any questions, just ask in the comments. And yeah, hopefully I'll see you again in the next video.